For centuries, humanity looked at the sun and asked a simple question: what is it made of, and how does it burn? Coal would have burned out in thousands of years. Chemical reactions couldn't explain it. It wasn't until quantum mechanics entered the picture that we finally understood the true secret of the sun's fire. The answer lies not in chemistry, but in the strange, counterintuitive rules that govern matter at the smallest scales, a world where particles tunnel through walls, where probability rules everything, and where energy and mass are interchangeable. At the heart of the sun, hydrogen nuclei, bare protons, must collide and fuse together. But there's a problem. Protons are both positively charged, and like charges repel each other with enormous force. Classically, they should never get close enough to fuse. The temperature at the sun's core, around 15 million degrees Celsius, isn't even hot enough to overcome this barrier. But quantum mechanics provides a stunning solution: quantum tunneling. Particles don't have exact positions, they have probability waves. And those waves can leak through energy barriers, allowing protons to essentially teleport past the repulsion and fuse together. The first step of fusion in the sun is called the proton-proton chain. Two protons collide and tunnel through their mutual repulsion. In the moment of fusion, one proton transforms into a neutron through a quantum process called beta-plus decay, governed by the weak nuclear force. The result is deuterium, one proton, one neutron, bound together. At the same time, a positron and a neutrino are emitted. This single step is incredibly rare for any given pair of protons. It might take billions of years, but with around 10 to the power of 57 protons in the sun, it happens 10 to the 38th times every second. Once deuterium forms, it quickly captures another proton. This fusion happens far more rapidly than the first step. The result is helium-3, two protons and one neutron. As this fusion occurs, the binding energy of the new nucleus is released as a gamma ray, a high-energy photon of light. This gamma ray begins an extraordinary journey through the dense plasma of the sun, bouncing and scattering for thousands to millions of years before it eventually reaches the surface and escapes as the sunlight we see on Earth. The energy you feel from the sun today was created in its core long before human civilization existed. The final step in the dominant branch of the proton-proton chain is when two helium-3 nuclei collide and fuse. From this collision emerges one helium-4 nucleus, two protons and two neutrons, plus two protons that are released back into the plasma to potentially begin the cycle again. The helium-4 nucleus is slightly less massive than the four protons that went into making it. That missing mass, about 0.7%, has been converted into pure energy according to Einstein's famous equation, E equals mc squared. This tiny fraction of mass loss powers the entire sun and everything that lives beneath it. Heisenberg's uncertainty principle plays a crucial role in the sun's interior. This principle states that the more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. In the dense, hot plasma of the sun's core, particles are confined to small regions of space, which means their momenta, and thus their energies, are highly uncertain and can fluctuate to extremely high values. These energy fluctuations are part of what gives protons enough kinetic energy to approach each other, making the tunneling process more probable. Quantum uncertainty is not just a limitation of measurement. It is a fundamental feature of reality that powers the sun. Quantum mechanics describes particles not as tiny solid balls, but as wave functions, mathematical objects that encode the probability of finding a particle in any given location. When two protons approach each other in the sun's core, their wave functions overlap. This overlap is what makes tunneling possible. The probability amplitude of one proton extends into the region occupied by the other. The Schrödinger equation, the fundamental equation of quantum mechanics, governs how these wave functions evolve over time. Solving it for the proton-proton interaction tells physicists exactly how likely fusion is to occur at a given temperature and density, the very calculations that tell us how long the sun will live. Every fusion reaction in the sun produces neutrinos, ghostly quantum particles with almost no mass that interact with normal matter only through the weak nuclear force. They are so weakly interacting that they pass through the entire sun without being absorbed, and then pass through the Earth as though it were empty space. Right now, 65 billion solar neutrinos are passing through every square centimeter of your body every second, and you feel absolutely nothing. Detecting these neutrinos was a landmark achievement of physics, and their measured properties have confirmed our quantum mechanical models of solar fusion with remarkable precision.